So first consider the three functions that we have here. First, if we have the polynomial 3x to the 5 minus 2x plus 1, and we're going to find the derivative of that. Applying the sum rule, we get that this is the derivative of 3x to the 5 minus 2 derivative of x plus the derivative of 1. Could actually put down out this 3 out of here and in front. And so now this will be 3, and the derivative of this will be 5x to the 4, since I put down the 5 and subtract 1 of the 5. And here the derivative of x is 1, and the derivative of a constant is 0. So the first one is going to yield 15x to the 4 minus 2. Now, for the second one, we have the derivative of 7 e to the x minus 2 square root of x, but I can represent that square root of x below as x to the 1/2, right? Or I can just put it on the top and see it as x to the minus 1/2. That way I convert the root into a power and I put it on the top. Now this is going to be 7 times the derivative of e to the x minus 2 times the derivative of x to the minus 1/2. Okay. Now this is going to be 7 times e to the x, since the derivative of e to the x is e to the x, minus twice. And then now we have a power rule here. We put down the minus 1/2. We leave x to the minus 1/2 minus 1. And that's going to be the full power rule for this. But then, if we simplify a little bit, you can see that this minus goes with this minus, becoming a plus. 2 goes away with 2, so it becomes a 1. And this is going to be x to the minus 3/2. Okay? And this can be pretty much the end for this if you want to. If you want to re-express this as root, then you can just write it again as 1 over square root of x cubed. Okay. Now let's go to the last of this ones, which is going to have a very similar transformation. So we have the derivative with respect to x, and now we have a cube root. So I can write a cube root as x to the 1/3 plus 4 over x, but now that x I can write as x to the minus 1, so it's a power as well, minus 11. So now I have everything in powers, and I can apply the sum rule. This is just going to be twice the derivative of x to the 1/3 plus 4 the derivative of x to the minus 1 minus the derivative of 11. Now if we apply directly the rule to this, notice that we're going to put down the 1/3, so it's going to be 2 times 1/3 x to the 1/3 minus 1, and then plus 4, right? But if you see the power is going to put down a minus 1, so we're actually going to get minus 4, and then x to the minus 1 minus 1 is going to become x to the minus 2. Now I can simplify this a little bit more. This is going to be 2/3 x to the minus 2/3 when I add 1/3 minus 1, and minus 4x to the minus 2. If I want to write again this as positive powers, I can't. This is going to be 1 over cube root of x squared. And this one will be minus 4 over x squared. And that'll be the end of this particular set of examples. So now let's move on to do another example, but let's take high order derivatives. So now let's consider the function f of x equals 3x cubed minus 5x squared plus 6x minus 7 over x plus the square root of x plus 2e to the x. So a mix of everything. So now let's calculate the derivative of this. So f prime of x is going to be, this is just a sum, big sum. So derivative of the sum is the sum of derivatives. So we're going to take the derivative of everything. So now this is just going to be the derivative of 3x cubed minus the derivative of 5x squared plus the derivative of 6x plus the derivative of, or minus, if you will, this one here, of 7 over x, and let me move this here, plus the derivative of the square root of x plus the derivative of 2e to the x. Okay, so we're going to apply the constant rule directly now, and we're going to apply the power rule directly now. Okay, so if we're doing this power, we're going to put down the 3 and we're going to subtract 1. So now this is just going to be 9x squared. Okay, directly. Same here. This is 5x squared, so it's going to become 10x. This is 6x, so it's going to become a 6. This is 7 over x, so this is just going to become 7, and this is x to the minus 1, right? So it's going to become x to the minus 2, and with a minus in front, plus, so 7 over x squared. Now this one, this is x to the 1/2. So remember that essentially this becomes 1 over 2 squared of x. And finally, the last one, the constant is not going to alter the exponential. It becomes twice e to the x. Okay. Just quick mention here in case you're lost with the 7 over x and the square root of x. Just remember that 1 over x is just x to the minus 1. And so just as we did in the previous exercise, the derivative of this is minus 1 x to the minus 2. Or this can be seen as minus 1 over x squared. And similarly, in the case of the square root, square root of x is just x to the 1/2. So if you take the derivative of this, you're taking the derivative of this, and this is just 1/2 x to the minus 1/2, which ends up being 1 over 2 square root of x. Now, just with that in mind, now we can go ahead and take the second derivative. Now, for that second derivative, maybe it was better to have some of these things in the original form that I was using for the derivative. So maybe instead, let me just write again everything in powers. So 9x squared minus 10x plus 6 plus 7x to the minus 2 plus 1/2 x to the minus 1/2 plus 2e to the x. This form, since it's in powers, is going to allow me to do second derivative much more easier. So f to prime of x now is going to be 18x minus 10, which is the derivative of x, 1. 6 becomes a 0. And now this one here, x to the minus 2. So the minus 2 multiplies, and this becomes a minus 14. And I subtract 1 here, and it becomes a x to the minus 3. Now, similar with this case, we get minus 1 over 4. And then it's going to be x to the minus 1/2 minus 1. So that becomes minus 3/2. We also did this before, so I'm doing it quickly this time. And now finally, this is going to be 2e to the x. There's no change at all. So we can simplify. We obtain 10x minus 10 minus 14 over x cubed, and minus 1 over 4, and then the root, the cubic root, the square root of x cubed over here, and plus 2e to the x. Okay, and so that'll be my high order derivative in this case.